So we've been looking at radioactivity, learning about the nuclei and all the transmutations. Did some measurements in the lab. Hopefully today's lab folks have a good time. And then now we're going to be talking about the health effects in nuclear medicine. So there's negative effects of being impacted with ionizing radiation, but there's also been a lot of positive things that we've used radionuclides for. Almost, I could probably say all, but I always hesitate to say all because that means everything, but almost all of our biochemical pathways were determined using nuclear radionuclides. So they would put a radioactive phosphorus in there and then track where phosphorus goes in the body or in the cell. Same with the, some sort of tag on the carbon or tag on the nitrogen. So we've used radionuclides to trace out all of our biochemical reactions. And so that's how they know Krebs cycle and the citrus acid cycle and all these different cycles. So let's look at our sources of exposure. So this is sort of broken into two columns. I'm missing my pen for a second. Where the column on the left is just the different sources, cosmic radiation and the earth, the minerals in the earth, bricks and mortar, human tissues and air. Potassium 40 in our body is a radionuclide, so we are irradiating ourselves just with our diet. So we're eating things that have potassium 40 in them. Potassium 40 decays and becomes argon, so that's where the argon concentration in our atmosphere is coming from. So then just from air, the radon exposure and air. So total natural sources in a given year, this is millirem per year. So 126 millirem per year just from natural sources. If you work in the Capitol building in Austin, it's higher because the granite there is above background. It's radioactive. So the quarry that they got that red granite from is, I guess it has uranium and thorium in it. And so it's got a small amount of radioactivity in it. Everybody talks about the Texas Capitol radioactive if you go on a tour, and it is, but it's still pretty low. So then for man-made sources, we have X-ray diagnosis. Of course, that's going to be more if you've had X-rays and less if you haven't. So that fluctuates quite a bit. It's also going to be more if you have, I always felt weird. I'd go get a dental X-ray and they'd take like 3 X-rays, and I'm thinking I'm getting irradiated, 3 little blasts of X-rays. If you go into a heart catheterization, have you heard of that procedure? It's they put a little probe, they go in your artery by your leg, and they go all the way up this vein, actually. They go up the vein, and they come into the heart, and they squirt some contrast fluid and watch the flow through your heart. So they've got this little probe in there that's squirting the dye. It's not really a dye. It's like a heavy metal, so that it can absorb the X-rays. And so it'll squirt through the heart, and you can see the valves working and everything like that in the X-rays. So what they do is they have the patient on this thing, and then they've got this X-ray machine that can spin around them, and it's taking an X-ray video. Like quite a few frames per second because they got to get the heart rate going. So your little 3 dental X-rays, that's nothing compared to a catheterization CAT scan. I mean, they're just blasting you with 60 frames a second of X-rays. Yeah. And anyway, so that year, if you get a heart catheterization, your dose is going to be high for that year. Radiotherapy. What is radiotherapy? Well, remember we talked about alpha particles having a really small distance of effectiveness, and they can make these little capsules that have alpha emitters in them, and they can stick them into cancer. So this even goes back to Marie Curie. Like they figured this out right away for prostate cancer and other kinds of cancers that are easy to localize. They put these little needles in there, and they stick in these radioactive seeds, and then they pull the needle out, and they put the seeds of radioactivity in the cancer cells and burn up the cancer cells. So that's radiotherapy. Again, it's going to be high if you're having that, and 0 if you don't. Nuclear power. Notice how this one is so small. We'll talk about nuclear power in a future lecture and why it's so small. But it's mainly because we want to contain all the radioactivity. So we have a lot of shielding in the nuclear power industry. TV monitors. My mom would always My mom would always say, "Don't sit so close to the TV because it puts out radiation." And she's not lying. Okay, she's heard that. What is it? Well, the old TVs had it was a cathode ray tube, so electron gun. So they're spraying electrons at the phosphors on the screen, and some of those electrons are going to knock out 1s electrons in the things that they hit, which is going to then have X-rays emitted. So there'll be small amount of X-rays coming out of a cathode ray tube. So yeah, so I guess mom was right, but it was very, very low amount of X-rays. But still, now we don't have the cathode ray tubes anymore. So I don't know if flat panels, I don't know any mechanism why flat panel would emit X-rays, but still. And then radioactive fallout. That's just from atmospheric testing back in the day, blasting these radionuclides, tens of thousands of feet into the sky and circling the globe. And so that's, I guess there's still some radioactive fallout from 50 years ago. So the total is only 193 millirem per year. And so radon can add, if you're in a radon area, it can add 200 millirem to that dose. So, that's doubling the dose if you live in a radon area. So what are the radon areas? Well, here's the fraction of homes that have 4 picocuries per liter of radon in that area. And so we're pretty safe. Down here, look at this, 0. That's nice. So here we are. We don't really have a radon risk in Texas, but you get the Rocky Mountains, and then up here in the Midwest, and then up here in Pennsylvania. Those are the hot spots, and it's just wherever uranium is in the mountains. So deep in the even some of the mountains, like I remember going to Oklahoma, and they were talking about, is it the Arbuckle Mountains? Anyway, they're just like hills. Because they're like, well, they were mountains, millions of years ago, they were mountains, and they eroded away. But, so there could be mountain ranges under the ground that you don't even know about, right? So there's, like up here in the Midwest, it's not necessarily known for a mountainous region, but those hills are just ancient mountains that contain a lot of uranium, apparently. Now, why did it become a problem? Well, because we sealed up our homes, and so the radon percolates through the bedrock and the soil, and then it will eventually saturate the concrete and come through the concrete. So it's a noble gas. So it doesn't chemically bond to anything. So it's not going to get stuck to any substance. It's going to just go through the tiny little pockets of space between all the substances, and it's going to migrate its way wherever it wants to go. It's a diffusion. It's going to diffuse through the soil. And then if your house is sealed, it gets inside, and then, it starts to concentrate in the house. So for homes that are in these red zones, and maybe even some of the yellow zones and so on, they'll have a little radon detector in the basement. It is a heavier gas, so it will stratify, and it'll be in the basement more than anywhere else. And so then our cousins were in Pennsylvania for a while, and they had a little radon detector in the basement, and they had a little vent tube that would exchange basement air with the outside. So that helped lower their exposure. But that's where the clothes washer was, and the ping pong table, and so your kids are down there playing ping pong and getting radon gas in their lungs. So we've discussed the difference between alpha particles and beta particles and gamma rays, and you can really discuss them in how they penetrate the body. Alpha particles are easily stopped by the skin, but if you ingest them, then they're on the inside of the body and irradiating your tissues, and that's not good. These are the real risks. Rapidly dividing cells are affected the most. So children, babies in the womb, and also cancer cells. So cancer cells are dividing rapidly too. So it's weird. Radiation can cause cancer, but it can also destroy cancer. So it's kind of a strange thing, but it is. I don't know what it is about the cell. I'm not a cancer researcher that radiation breaks and causes its reproduction to just kind of go haywire. So it just starts to reproduce without any control. But it can also then destroy that cell. But we live in a radioactive world. I mean, all electromagnetic waves are technically radiation, but we have this cutoff of water being ionizing radiation. So here's our acute biological effects. We talked about this a little bit last time. If you get up to the 25 rem threshold, then you start to see a slight temporary decrease in white blood cell counts. Radiation sickness, I think that would probably kick in at 100. It starts talking about nausea and a decrease in white blood cell count. And then the LD50 is 500 rem. So are y'all familiar with LD50s? Have you heard that term before? 50% of the population. So that's it's at 500 rem in a given population. Let's say this room is there's a criticality event and they calculated we got exactly 500 rem, then the expectation is half of us would die. Yeah. And so if you're 10 times that, the expectation is that 100% you're going to die. There's a great film, if you're interested in this, in the sort of the Manhattan Project and the bomb programs, called Fat Man and Little Boy, and it's about the making of the 2 nuclear bombs that we used in the war. The little boy was the gun type weapon that used uranium, and the Fat Man was the implosion weapon that used plutonium. So it's just a great video. And so they were testing the purity of the radioactive pieces of the plutonium weapon, and there was an accident. The guy was bringing these 2 hemispheres together and measuring on a Geiger counter how radioactive they were, and he was using a screwdriver to measure the gap between them. And he had all these lead bricks around him, so he was protecting himself. And the screwdriver slipped, and the things went together, and it was starting to go critical. And he reached in with his hand, and he pulled them apart. And he saved everybody in the room but himself. Yeah, and it's really dramatic in the movie, but it is a true story that happened. And so then he got a lethal dose, even through his hand. Okay. And so it's sad because he says, stop, and he pitches chalk to everybody in the room, and he says, mark where you were standing, take off all your metal, and leave. And so they all left, and then he stood, because he knew he got the biggest dose. He stood in there, and he did on the board the distance, and he had a measurement device, so he knew what the counts were. There's like this many counts at this distance, that distance, that distance, and then he says, everybody's going to make it but me. Like, he was able to calculate his lethal dose, and he knew he had gotten one. And it's a really sad part, and he does die in the movie. It's pretty sad. So that's a spoiler. But yeah, but it was interesting. Yeah. So that's so here's the thing. Why do you tell them to take off their metal? Well, but that many gamma rays come out. Gamma rays can activate other metals. They can hit those or other nuclei. But metals have the larger nuclei typically. Your carbons, I mean, that's a small nucleus with only 6 protons, 6 neutrons. But look at iron 26, and it's a bigger nucleus. Iron's more abundant. So all your metal and your belt buckles and everything like that, they contain iron. And iron has a real pesky thing. If it gets irradiated with gamma rays, it gets excited, and it doesn't fission or break apart. It just re-emits more gamma rays, and then that ionizes nitrogen in the air. So iron is a tool for, I guess, making radiation events worse, I guess is what I'm saying. And then your body's full of iron too. So let's look at some of the reactors and what happened. Do y'all remember this? I don't remember what year it was. Does it say? It doesn't say. But there was a tsunami in Japan. Do y'all remember the story? Or have y'all heard of this? So the tsunami in Japan, and then the tidal wave, well, it was an earthquake that caused a tsunami. And there were these reactors at the Daiichi plant on the coast. They had 5 reactor buildings, I believe. 2 of them were fully, in operational. I think the other 3 were down for maintenance. But they had the backup generators and so on. I think it was ridiculously high tower, like 5 meters up, but the tsunami was like 5.5 meters. At 2011. I can't believe it's been that long. Yeah. So I don't think there was a movie about this one. Chernobyl was the one in Russia that completely blew up. This reactor, so let me just tell you, it was 2011. So this So the earthquake cracked this wall right here. I'll just draw it right here on the side. So it cracked right there. Now, why is that a problem? Here's the reactor pressure vessel. It was totally fine. As soon as there was an earthquake, the sensors in the power plant said stop the reaction. So they dropped in the control rods. Everything worked perfectly. Okay, so then the reactor starts to cool down. Okay, now in one of them, this suppression pond, this water pond down here, cracked, and so it was losing some coolant, and so that one did it. The reactor worked well, but the coolant failed, and so then the reactor did melt down. But up here, this was the real problem. This is spent fuel, okay, and it holds the hot fuel until the processing can safely take place. So when they swap out the fuel, they put the hot fuel in one of these storage pools where it can decay for a while, and those really short-lived half-lives, like when we were doing the fission reaction, we ended up with the strontium, and it was like 107. And what is strontium's normal mass? It's like 87. So it's got to shed like 10 to 20 nucleons. So it is extremely radioactive, and that's going to have a really short half-life. So in the first year, a huge percentage of the radioactivity goes away, and it becomes much less hot. But you got to keep the spent fuel cool. So we've got pools of water in there that are keeping it cool, and that spent fuel pool, it's so hard to say, had a crack in it, and that water level was starting to leak out. And so where's your pumps? Your pumps are on the diesel generator that just got shorted out by the seawater. And so they couldn't get the power put back onto the pumps to get that spent fuel pool cooled down. And so the water level dropped and dropped and dropped until you started to expose that metal. Remember our thermal conductivity chapter? The water has a huge thermal conductivity. It can keep that heat away. As soon as it drops down and you just have air, the thermal conductivity is really slow, and that metal starts to heat up. It glows red, white hot, and then it gets so hot that it can do the reverse of the hydrogen-oxygen making water reaction. It thermalizes the water. So the water breaks into hydrogen and oxygen at the perfect stoichiometric amount, right? So this started filling up with the perfect stoichiometric amount of hydrogen and oxygen, and all it's right there. It was just building up, building up, building up until there's a spark or some kind of auto ignition, and then it blew the top of this building off. It didn't damage the concrete. It just blew this metal superstructure off. And you can go on YouTube and find the video. This top of this roof just blows off. They knew that there's a reaction that's about to happen. They're like, we've got way too much hydrogen and oxygen. We're going to have an explosion. And it blows the top of that building straight in the air. It's like, it just goes straight up, okay? And then it, falls back down on the plant. So what about the worker exposure? The press, this is a scary thing. We got this power plant that we can't cool down. The press beat the drum that the workers at this plant were standing in their graves. Because that pulls at your heartstrings. These brave people are trying to get this situation fixed. They're the only ones that know how to do it, and yet they're getting irradiated and they're going to die. And everybody on the news it was just so sad to hear all these stories about how everybody's going to die that's helping fix this problem. No one died. No one even received 25 rem, okay? No workers went above 25 rem. Okay, one female worker received 1.7 rem. That was above the limit for female workers of half a rem each 3 months, but there was no impact on her health. The radiation controls, of course, differ between male and female workers because of possibility of an unknown pregnancy. There were 201 people working at Fukushima, and the Daini plant right next door had 645 people, and nobody went over 25 rem. 30 went over 10 rem, okay? Which is, again, that's a big dose compared to, your everyday working conditions when you like burn up for the year if you go over like 2 rem, and they got 10. So it's like they got 5 years of their maximum administrative dose, but it still wasn't above the health effect dose. And so even though this was the reality, Germany and Fukushima, Germany decided to phase out all of its nuclear power activities because of the hype from the press. So it's just really sad. And we'll talk about nuclear power in a future lecture about why it's so clean and safe. Well, if you're going to build nuclear power plants and then operate them, or any kind of power plant, these are the deaths per 1,000 terawatt hours, or 3.6 exajoules of electricity generation. And so for that many exajoules in a coal-fired power plant, there are 100,000 deaths in building, operating, maintaining coal-fired power plants. Oil, 36,000, natural gas, 4,000, and nuclear is down here at 90. So if we were to use all of these for our worldwide consumption, let's say we put everybody in the world on a coal electricity, we would have 11 million deaths per year from coal, and we'd have 10,000 deaths per year from nuclear. So anyway, and then here for oil and for wind. So even wind would have more deaths than nuclear. And you can imagine, I mean, you're trying to maintain those turbines way up there. So let's talk about now this top of this radioactive explosion. This metal comes back down to the earth, lands, you got to clean it up. Okay, how are you going to do that? Because it is really hot. Some of this rubble was 30 rem per hour. Remember, our threshold is 25 rem, a year, I guess, and this is 30 rem every hour. So you would get a threshold dose in trying to clean it up in 1 hour. Other degree patches were 3 to 4 rem per hour. Okay, the overall site was less than 0.06, so 60 millirem per hour. There were some hot water pipes, and some of the air levels were, up to 2 rem per hour. So they scooped up all of this debris and they carted it off to a storage facility using robotic, backhoes with pinchers. Yeah. So the RC kids are like, yeah, send us in. So they have radio controlled dump trucks, radio controlled picker uppers, and they go in there and pick up all the debris, throw it in the dump truck, they measure their radioactivity, say, oh yeah, it's hot. Let's go take it to a storage facility. So it's kind of interesting. So let's talk about this health theory. There was, obviously, about the Cold War, right? You probably heard about that, your parents, and yes. And so my parents, and also even a lot of my life, some of my greatest fears as a middle schooler was nuclear war with Russia. I had nightmares about it because we lived right next to a Air Force base that had B-52s and part of our Strategic Air Command. And so these bombers would be going over the North Pole to bomb Moscow at a moment's notice. And so I just knew that I would, they would call us and say, you got 30 minutes, make your peace. And so this back and forth and saber rattling, we would have a set of nuclear tests out in the Pacific. We'd set off 10 bombs and measure whatever it is we're measuring, and Russia would do theirs. This island up above Siberia, and they would set off 30 bombs, and we'd set off 40 bombs, and just kind of showing back and forth how much power we had in terms of our stockpile. Well, what does that do? When you have a nuclear detonation in the air, in the atmosphere, it's incredibly hot, millions of degrees of heat, and the air around it is cold. So the cold, dense air displaces the hot air, and you have that mushroom cloud. So that's what the mushroom cloud is. It's the heat that's rising. And then it gets up there and it expands, and then it continues to rise if it's still hotter than the ambient air around it. So that's why you have that shape. It's nothing directly tied to a nuclear blast. You can have a conventional power plant explosion or chemical plant explosion and still generate a mushroom cloud. Maybe you've seen some of those. I see them. I've clicked enough of them on Instagram that I see them all the time. It's like, oh, what was this? Oh, a propane filling station blew up in some town, and you can see this mushroom cloud. Looks like a nuclear blast, but that's that heat rising. That's what's causing that mushroom cloud. Well, if a nuclear blast it sends up those radionuclides up into the atmosphere. Now that's actually, if you're going to blow up a nuclear device, diluting all of the radioactivity over this enormous atmosphere lowers the local dose dramatically. Okay, it does put all that nuclear pollution in the atmosphere, though. So it caused the whole world. They're like, hey, you people, you Russians, you Americans, French, Great Britain, all the countries that had nuclear weapons that were testing them in the atmosphere, they're irradiating the whole planet. And so Greenpeace and the UN and a lot of people were like, hey, we need to stop this atmospheric testing. So they came up with this theory called the linear no threshold test. So the traditional theory of toxicology is that doses below a certain threshold can be handled by the body. And we talk about that, the toxin being the dose. So, if you have a tiny little dose, it's the body can manage it. If you have a larger dose, then it starts to show some health effects. But the threshold theory that doses are not additive. So like if I get a dose today and my body resets and I get another dose in the future, my body is already reset from the first dose. The second dose doesn't add. So I don't add the doses. So traditional toxicology says the doses are not additive. And then this one was related to nuclear radiation, that hormesis proposes that a small dose of radiation is actually helpful for culling weak cells. That one is, I put it on the traditional side, mainly because people that hold a traditional view of toxicology would, if you hold a hormesis view, you also would hold a traditional view. So those go together, although they're not exactly the same. This one is somewhat controversial. Some people say, no, radiation is damaging no matter what. But others would say, yeah, it's damaging to all cells, but the weak cells get culled. So it helps eliminate weak cells. But anyway, so I'm not going to die on the hill of hormesis. Okay. But now let's look at the threshold. The linear no threshold theory. This says all doses are detrimental, no matter how small, and that doses are additive. And that this was used, those 2 points were used to play a political role in enacting the atmospheric test ban treaty. It was definitely a scare tactic in a sense to say, well, let's get the power of the whole populace of the world to complain and stop this atmospheric testing. So probably in general a good thing. Okay, but the bad thing that came out of it, it's good that we stopped testing in the atmosphere. But the bad thing is that this scare tactic over radiation being somehow unique has been maintained to this day. So think of these are ridiculous examples. If the linear no threshold theory were applied to other kinds of situations. So you've breathed automobile exhaust. That means you've been exposed to carbon monoxide. Okay. Now, on the left-hand theory, your body has reset from that exposure. So you get another breath of carbon monoxide, it's harmful to you, but it doesn't add to the previous exposure. So linear no threshold theory would say eventually you're going to go anoxic because of CO. If you let's say you work in a building and you have a parking garage and you walk through that garage every day, you're breathing in carbon monoxide. So eventually one day you're going to walk in there and you're going to just die from carbon monoxide poisoning because you've gone in there for 50 days in a row. But that doesn't acknowledge that over the evening at home or whatever, that you've processed out that carbon monoxide and recovered. So the linear no threshold theory takes no account for the body's ability to reset and metabolize or eliminate the toxins. The other one too, have you ever swallowed wrong or gotten water in your lungs? The linear no threshold theory would say you would eventually drown. Like you swallow wrong that last time and then you're dead, But no, we know that the body can get the water out of its lungs and reestablish equilibrium. So the linear no threshold theory is just wrong, but it's definitely applied still for the radiation folks. And so be sort of tune your ears to that if you hear somebody arguing against nuclear power or any kind of radioactive elements. Listen to see what their arguments are, and sometimes it's this. Not always, but sometimes it's this. So how does our body really work? Well, absorption, distribution, metabolism, elimination. So we absorb the toxins. We have normal environmental input as well. Then it's distributed over the body, okay? and then we metabolize it, and then we eliminate it, either through our feces or through our pee or through our sweat or through our breath. These are ways that we get rid of toxins. Now, radiation, external exposure to radiation, is governed by time, distance, and shielding, and it's not metabolized. It's not a chemical that needs to be metabolized. What it does is it damages tissue, and the tissue needs to be dismantled. So if you have a cell that's, let's say something happens to a cell membrane, and now it leaks and it dies. So you've got a dead cell. It still has a lot of molecular machinery, the DNA, the ribosomes, all of those things. They need to be dismantled. And so those, the body, your immune response, and your inflammation and all of those things kick in, and they dismantle the damaged tissue and reset the body. That's where your nausea and your fever come from. If you've got a bad radiation dose, then you can elevate your temperature, your body temperature, to speed up the rates so that you can get rid of the damaged cell tissues. I got a sunburn so bad that I got a fever. So I felt very flu-like after being out in the sun when I was a little kid. So I just got totally, like a cherry tomato, and it was bad. So this is the normal toxicological treatment. That 50 LD50 is that expectation of 50% of the population dying. But we have these other levels too. The lowest adverse effect level, okay, and then the no observed adverse effect level, and then down here is 0, the no effect level. But this was 25 rem for the yellow line there, the lowest observed effect level. And here's all of the biological half-lives of toxins that you know about, like mercury, benzene, styrene. This is from a chemical industrial health book. And how to test for them. Like mercury would be tested in the blood, and it would be in the blood for 1 week. You could test it up to the blood, and in the urine for several months. So this is a log scale down here. Look at cadmium. The half-life, the biological half-life of cadmium in the body is over 10 years. When you get cadmium in your body, it's there to stay. Anyway, there's no entry for radiation because it's not a substance that can be absorbed, distributed, and then eliminated. Now, there may be radionuclides, like you might have radioactive nickel, and it's going to be in your body for less than a week. Well, half-life, So 10 weeks, you would be rid of all of that nickel. But that's bad if it's radioactive nickel because it's in your body for 10 weeks, irradiating your guts. Now, is it the radiation from the nickel that's hurting you? It's destroying your tissues, and your body's trying to manage the destroyed tissues. Now, some people will be like hypersensitive to certain toxins, right? You might have an allergy to tree nuts or something like that, or latex, and that's kind of an immune response to your body, that your body's going crazy when it gets exposed to those things. And in terms of these long-term substances that accumulate in the body, they might cause hypersensitivity or health effects. And then there might be people who are not able to metabolize or kill damaged cells or cancerous cells. And we would identify those people early because you've probably had cancer already. But you're a young person and your body recognizes it as foreign. Because a lot of times when the cancer cell is rapidly dividing, it doesn't express all of the membrane proteins the same way as a normal cell. And so the body sees this cell membrane, and maybe this protein doesn't have the sugar coating it should have, and it identifies this cell as foreign. And so in come the killer T cells, and they kill that cancer cell before it can ever get out of hand. Your body has a pretty rapid immune response to these things, but it tapers off over time. So if the cancer survives that initial onslaught of your immune response, then it can get a foothold and grow. So you've probably all had cancer. The fact that you can fight it off is evidence that you don't have cancer now. So those kids that get cancer early in life and don't have this immune response to cancer, they get cancer right away. And so that's why you have little kids like my cousin's kid who is, I forget what age, 7 or 8, and he had leukemia. And they finally, he's now cancer free, but it's like something was wrong. He got cancer and it got past his immune response, or his immune response for whatever reason was weak against cancer. So there's no way for us to accumulate radiation like we accumulate cadmium. Okay. We get radiation doses externally all the time. We might get internal radiation doses from like potassium 40. If we can't metabolize those things, we know it already, because we would be a child with cancer. Okay. And then radon gas. It's one of those ways we can get internal doses. So this is our transuranic series. It percolates through concrete, and it's probably responsible for up to 14% of lung cancers. So here's some useful radionuclides like the iodine 131. We can use that to scan for things like hypothyroidism. So if we can, thyroid collects iodine, so we put radioactive iodine in the body, the thyroid is going to glow like crazy. So how do we image it? Well, we have these phosphors that can measure the radioactive particles coming out of the iodine, and then we have these photomultiplier tubes, and then we just have these lead collimators. So the image is sort of a planar image of our thyroid. So it looks like it's coming from his shoulder, but it's trying to show that his thyroid is in his neck. Okay? And so it's getting a medical image. We use technetium-99 to image the heart, and apparently some of these others, eyes, liver, tumors, and so on, for phosphorus 32. So these are all of our radionuclides that we use in radiomedicine. Here's the best one, though. I love this one. This is the positron emission tomography. We can put this sugar, this carbon-11, into sugar molecules. Cancer cells love sugar because they're dividing, building substructures. And then it spits out a positron, which then reacts with an electron. Okay. And it annihilates to form 2 gamma rays. So this is a 2 gamma process that is simultaneous. And so let's say there's a radioactive potassium here and it spits out a gamma ray, but there's no gamma ray on this side. So momentum is conserved. So if a positron and an electron hit each other, the gamma rays go out in opposite directions at the same time. So the computer can look at all of these detectors, and if it never gets 2 simultaneous ticks, then it ignores it. So we can have radiation hit this detector here, but there's no corresponding detector on the other side that got hit, so the computer throws that out. And a cosmic ray comes in from outside and hits this one, and the computer looks on the other side and doesn't see a simultaneous hit, so it ignores that one. So this is high contrast. It's able to take the background at 0 and only see the positrons where they come out. And because we put them in a ring, we get a hit here and here and there and there, and we know that the hot spot is right there in the brain. And so this is a really fascinating technique. So I'm really big on PET scans. Because it's such a low background, we can reduce the amount of radioactivity we give people. And that's also a good thing. We're going to talk about nuclear power in a future case, but after we use the nuclear reaction, we generate a lot of medically useful radioisotopes. And so this is a research reactor. So down there in the bottom is the nuclear power plant, the nuclear reactor, and then all these tubes and stuff and cables and everything. We drop things down in there to irradiate the heck out of them. Okay, so we can create radionuclides in our nuclear reactor and leave the fuel there and put stuff in between it or around it. And just kind of like the bank teller, you put your deposit or your check in there and you punch a button and the air takes it over and puts it in the teller box. We do the same thing with nuclear reactors. We have these tubes, put your sample in there, shoot it down into the reactor. It gets irradiated like crazy. Punch a button and it blows it back up to you and take your sample out. And so that's how we get things in and out. Once we have our sample that's irradiated, then we use these things called hot cells, where this is really thick glass. You can see how thick that window is right there. And these are called manipulators. And you can like unscrew jars and manipulate things with these little handheld deals. So it's not exactly robotic. It's more like exoforce. Like you've got mechanical hands that are inside this hot cell, and you can do things with them. Okay, so that's how we protect our workers dealing with highly radioactive materials. So here's an example: 1, 2, 3, looks like 4 hot cells together. So your workers, so I mean, this helps you avoid the glove box thing, right? They used to use glove boxes, but the gloves would leak and they wouldn't have enough shielding. And so if it's really highly radioactive, you have to back out and just use mechanical hands. But we can work with this stuff. We've been doing it for decades. So next time we'll talk about nuclear power.